All right, we're back for day 12 of Advent of Code. And here we go. Oh boy. Total price of fencing all regions. Okay. Price of fence, area by its perimeter. Okay. Cool. Connected components. Let's actually, we don't even need connected components. I think. Oh, just kidding. Yeah, connected components. And then if we've already visited it, then we're done. Okay, and then next. Okay, now we have all these, and then the perimeter is going to be a little bit annoying. I think. Okay, I have a way to find the perimeter. So let's do. Let's invert this thing. Okay, now we have mapping of the connected components. And then now what we're going to do, this should be a set. And then first the area. That's easy. And then the... oh, wait. Its boundary with each X region contributes an additional 4. Oh, that's fine. Okay. So the area is this. And then for the perimeter, what we're going to do is for n in nodes. For every adjacency, we're going to check. We're going to move one step in that direction and see if it's not part of the object. Really hope I'm not. Oh god, I am using n. Shoot. Okay. Or nx and y not in nodes, then add 1 to the perimeter. Why is this taking forever? That's not great. Shoot. Okay. There's a number. Total price, rank 205. Okay. Bulk discount. Instead of using the perimeter, use the number of sides each region has. Ooh, this is annoying. What is the best way to do this? I guess whenever we get a segment. No, it's not going to work. Yeah, I'm a little stumped at how to approach this. I guess we can can at least get a list of the perimeter. The perimeter is between node and an x and y. So that tells us where the perimeter edges are. And now we want to reduce it in a certain way, such that I think we can, we can move both of the perimeter nodes by 1. So I guess first we do want to like normalize this in some way. Perimeters are flipped either way. Yeah, so let's normalize it by, what happens? I have no idea what happens in a certain really weird case, but I'm not gonna worry about it for now. I'll worry about that later if it's wrong. So what I'll do, let's normalize this. No, that's not what I want. Is that what I want? I'll add it in both directions. And then what we'll do is we'll try and combine things. So for P1, P2 in her, the question is for dx dy and adjacency4. Technically, I don't want adjacency 4. I want only a subset of these. I'll explain what I'm doing after. It's a little complicated to talk while I'm doing this. Okay, and then so we'll transpose both of these by this, P1 new, be very careful not to write a like typo something dumb here. If P1n, P2n in her, and then I think it's len per 2 over 2. Ooh, it does not like that. Oh, that's because I made this a list by accident when I was going to normalize it. I forgot to make it a tuple again. Okay, let's try this. No. Now let's try the sample input and see what's going on. This map has a total price of 368. So let's print out the area and then what I think the perimeter is. This should be double the thing. Okay, so I see 2 regions. 2 regions? I see 3 regions. Okay, 16, getting 4 for the number of segments here. Wait, did I actually read it correctly? Number of sides each region has. Yep. Okay, and then in this, 2 regions full of type B plants, each with 4 sides. Do we not need them on the edge? Inside and outside. So the fence does not connect across the middle of the region where the 2 B regions touch diagonally. Okay. 4 sides on the outside, and then 8 more on the inside. 8 more on the inside? What is this? Oh, this is the A region. The A region has 1, 2, 3, 4, and then 8. Oh, I'm deduping these. I care about the directionality of the perimeter. Okay, that is resolvable though. I think I get rid of this and I remove this. It was 368. Let me just double check. 8. I said there were 8 regions, so and there were actually 12. Yeah. So I think we just need this to be directed, and then we still do the deduping, and then we don't divide by 2. I feel like I shouldn't. No. Yeah, I think this is good. Let's check. 368. 368. Cool. And then there's my answer. Rank 16. Whoa! That is a high finish. Okay, well, I guess I know that the large language models just cannot do day 2 of today, which honestly is not surprising. I was puzzling over how to even approach this for quite a while. Oh man, feels good to get a high finish time on one day. Oh man, yeah. There are like no super fast times. I mean, this is a really fast time, but it's like reasonably fast if you know what you're doing. Oh man, 16. That feels good. Sick. I wonder how long it will take for this to fill up. Okay, now I can actually take a minute to explain what I'm doing here. This was a pretty involved problem. So the first part, we're given, yes, so first I'll explain what the question is. We're given some grid of letters, and we want to identify each region of contiguous letters. And then for that region, what we care about is the product of its area and its perimeter. And we want to sum that up across all regions. So this is a connected components algorithm. One thing I thought about doing at the very beginning, but I realized that I think the question does say it's to be careful of this. One thing I thought about doing was, maybe you don't need to do connected components if there's at most 26 regions because the letters are unique. This is not true. You can have regions like this where the letter X gets reused. So you do need to do the connected components algorithm. The connected components algorithm, for those who are unfamiliar, is basically just a depth first search. You start at some node and your goal is to identify everything that is part of this component. You can do this with really any graph traversal algorithm. I like using DFSs just because they're really fast to write. Some people do this with breadth first searches because they're really they have a way of writing DFSs which they like, but really either way is fine. But yeah, so what I do, I'm just doing a DFS, and I only continue if the grid cell is equal to the thing that we're trying to flood fill. So sometimes this is also called a flood fill algorithm when it's done on the grid. I guess when it's done on, yeah. Anyways, so yeah, I check to make sure that it's the same letter. And then I just recurse. And then CC here is my connected components. So this is a mapping from node to component number. And then the main loop here just looks like this. You just go through every single cell in the grid. And then if it hasn't already been traversed, then you start a new traversal there with a new number. So next is the next number. And then when you're done, you will have every node in this graph, or every node in this dictionary with whatever its component label is. The next trick is how do you figure out the area and the perimeter? So it's easy enough to invert this mapping and go change it instead to a mapping from connected component ID to the nodes that are in the connected component. And then once you do this, the area is easy. It's just the number of nodes in that region. The perimeter is a little trickier. One trick that I like to use here is for each node in the region, you can figure out what it contributes to the perimeter by, you go through each node. Let me make this bigger. Yeah, so let's look at these R's. Make these a little more visible maybe. So for each node, what we're gonna do is we check to its left, to its bottom, to its right, and to its above. And then we ask, is that cell in that direction also part of the region? If it is not part of the region, then there's a perimeter line. So in this case, it is not part of the region. Here, maybe even like MS Paint is like a good way to demonstrate this. But yeah, so first we check above, and above is not part of the region, so we add a line there, add one to our counter. Left is part of the region, it's this cell, so we don't do anything. Bottom is part of the region, right is not, so we add a line there. And then we just repeat this for every single thing here. And what we end up with is exactly the perimeter. So that's a cute little trick that I like to use. Works like a charm. What are the gotchas here? One is to make sure you handle things correctly on the boundary. So making sure that if you like go in this direction, it is something different. And then the other is, in order to do this check efficiently to see if this cell is like part of the thing, you really want this to be, rather than have a list of the nodes or the grid, the grid cells in this component, you want a set just to make the check really fast. And yeah, that's how you do part one. You just sum that up. Part two now says it's not actually the perimeter. What we actually care about is the number of like straight line segments, like so. And this will be like strictly less than the perimeter, or sorry, not strictly. This will be at most equal to the perimeter if all your little perimeter segments are like length 1. But there will be some times where you have like 4 lines in a row and it'll be less. And this is a little trickier. The way that I did this was I sort of used actually the same exact trick again. For each of these perimeter lines, what you do is you check to your, I guess, anyways, sorry, I like thought of a complication with the approach like halfway through explaining that and then realized why it's not a problem. But anyways, we check to the right and see like, is this line part of us, part of the perimeter as well? And then you check to the left and say, is this line part of the perimeter as well? And what you really want to do is you want to keep exactly one line along all of this. So what I did is I picked 2 directions, noticeably not adjacency 4, and I tried transposing my perimeters in that direction. And so what are these? 1, 0, and 0, 1. 1, 0 would be first index is row, so I think 1, 0 is this way, and then 0, 1 is this way. It doesn't really matter too much though, as long as the code is consistent, which it is. Or like, really you could pick any 2 directions that are orthogonal here. But yeah, so then I take this, I try moving it down 1. I don't see it down here. I try moving it right 1. I do see it here, so we delete this one. We ignore it. And then we repeat this process, and then if we do this, we should end up deleting everything except the rightmost perimeter in the case of horizontal perimeters, and the bottommost perimeter in the case of vertical perimeters. And then you will note that the number of these that are remaining is exactly the number of line segments that we use. So this is like really the same trick as the other one, just like more complicated and harder to think about. One thing you have to worry about when doing this is how do you actually represent perimeter line segments? This is pretty annoying. I chose to represent them as pairs of the 2 nodes that they border. And the first bug that I wrote was I was like concerned about directionality. Like if you have a segment that is like this cell, comma, this cell, even though this one's not real, and then you have one that is this cell, comma, this cell, they are technically the same, like they're on the same line. So I wanted to like dedupe them in a way. So I added both to my set when I was doing this trick, and then I just divided by 2 at the end. This is actually wrong because of the case. See, there's one in here. I don't think there's gonna be one in here. But if you have a case where you have a region that looks like this, let's make it bigger. If you have a region that looks like this, And I was wondering about this while I was doing it. I was like, not sure. Should this be one segment or two? And it does say something about like the Mobius elf company. I didn't read it too carefully, of course. I never get to read the flavor text, unfortunately. Oh yeah, I would have used the Mobius fencing company instead. Little Mobius strip reference there. But they're saying that this should not count as one. It should count as two. And because of that, you actually don't want to add both directions. You want to add just one direction. So you just be judicious about like which direction you choose, and that's fine. Like it is consistent. And then these will not dedupe each other, which is exactly what you want. Yeah, one thing that's a little weird with my solution is I mentioned that I try two directions for each segment, and I try this regardless of whether it's a horizontal or vertical edge. So it is the case that I will like take this edge and I will try moving it up one, or sorry, I forgot, down is the direction I'm checking. So I'll take this edge and I'll try moving it down one. It won't actually overlap because of the directedness. The direction of this edge is something like this. And then when we move it down, it's this direction, which is not overlap with the other one. So it does the correct thing. But I probably did not fully appreciate that when I was writing my code. I just sort of wrote a thing and it worked. So that worked out pretty well for me. I just got a little lucky there. But yeah, that is part 2. I guess I'll like very quickly clean up my code. Can't use P1, I already used that variable name. Part 1, part 2. Very easy to recover the part 1 code. And then this is part 2. Cool, and then I think that should be it. Those are my answers? Yep, they are. Cool. And yeah, that's part 2, Advent of Code Day 12. Let's check on the leaderboard real quick, see how it's doing. Okay, it's full now. Filled 5 minutes ago. Cool. Yes, 17 minutes. That's probably the longest one so far, I think. Although I guess I'm not sure. Was this enough points to take me back on the global leaderboard? It was! I'm barely on the global leaderboard now. Sick. As long as we get a few more of these days, maybe I'll be able to actually do some leaderboard climbing, which will be exciting. But yeah, that's all I have for today. I will see you all tomorrow.